Hey there, chemists. In this lesson, we're going to look at how we can take things like a ketone and protect it as what's called a ketal. This is an acid-mediated mechanism, so we will only see positive charges in the mechanism, and it's catalytic, which means the first step will be to pick up an H+, and the last step will be to remove an H+. You'll notice that we combine a diol in this, and that ends up becoming this piece of the ketal. And to balance this, we actually lose one equivalent of water. So let's see if we can figure out the mechanism for how this happens. Start by just redrawing the ketone. In this place, we're going to use just acetone. And the first step is just protonation of that ketone. There's only one thing that's possible. Protonate the ketone, and you get a positively charged carbonyl. This is actually called an oxonium ion. It's just a positively charged oxygen. And it's at this point that the diol comes in and forms a bond. So draw an arrow from one of the oxygens to the oxonium carbon and send that pi bond up to the oxygen. That gets you an intermediate that looks like this, with a plus charge on the oxygen that used to be part of the diol. So looking up above, how do we get to the ketal? Let's just sort of check in. We need to lose this OH group, and we need to form another bond between this oxygen and the carbon where that first OH is attached. We can't lose the OH as is. We need to turn it into a water molecule. We can actually do that in a quick acid-base step. If we use some conjugate base, let's assume we're in water. If we have H+, we have some conjugate base. I'm just going to use water, and it can take that extra H away, which is on the oxygen that's positively charged, and you turn it into a neutral intermediate that looks like this. This is actually called a hemi-ketal. We're sort of on the way to the ketal. And now I have an extra H in my medium, so I can protonate that OH that I can then turn into a water molecule and have it leave. So all of this is just to get that first oxygen to effectively get two H's on it, and now it can leave as a water molecule. And at the same time as it leaves, picture what's left in its wake. That would be a carbocation, but it's a very good carbocation because the oxygen right next to it can stabilize it through resonance. So I'm going to show that arrow right in the same spot. And when you do it, now you have a positive charge on the oxygen. You have yet another oxonium ion. So just to compare where we are with where we want to go, we need to form another carbon-oxygen bond, and we're now ready to do it. The other OH can form a bond with the oxonium carbon, push those electrons up to the oxygen, and here's how you get your 5-membered ring. We still have one too many H's, so the first step in the mechanism was to put an H on. Our last step is going to be to take it off. And anything could do it, but I'm going to use the water that we just created to take that last H off, and that's how you get your ketal. So that's mechanistically how we take a ketone and turn it into a ketal. There's one more thing I'm going to do in the mechanism, and it's just show that every single step is actually reversible. This is not crucial when you're writing mechanisms, but it's useful to think about if you're ever doing this in a laboratory, because it means you can take advantage of Le Chatelier's principle and drive the equilibrium in one direction. In this case, we'll take water and remove it as it's formed. There's equipment that we can do in the laboratory, that we can use in the laboratory to do that. It forces the reaction to go forward. That also means we can take a ketal and we can add water to it. And that's how you turn a ketal back into a ketone and remove the ketal. This is also done under acidic conditions, and we're using a slightly different ketal this time with two methoxys attached. So that means you're going to create two equivalents of methanol. So one ketal becomes one ketone and two alcohols. So how this happens is the reverse of the mechanism we have up above. It's still acid-mediated, so the first step is protonation of one of those oxygens. So you get an intermediate that looks identical to what we have up above, except that the oxygens are not attached to each other. And now we're set up to kick out an equivalent of methanol. And at the same time as we do that, we can donate a pair of electrons from a neighboring oxygen, and you'll make another oxonium ion, just like the one we had up above. And if you compare this intermediate with the one that we have up above, how do we make it? Well, you can't just lose a methyl off of an oxygen like that. We've got to turn this into a methanol. So here's where our water molecule is going to come in. So draw an arrow from that water molecule to the oxonium carbon, send that pair of electrons up to the oxygen. You get an intermediate that now has two oxygens, plus charge on the oxygen that used to be water, and then a methoxy attached to that. We're actually almost back to a hemiketal if you look at the structure. And we can lose the methoxy if we have it take one of those H's. In an ideal case, you would draw this as two separate steps. It's probably a solvent that takes one of those H's away, and then the methoxy picks up an H plus from whatever took the H in the first place. But we're going to take a shortcut here since these are so fast and reversible and just write H plus transfer and show it as if it's intramolecular. You're usually safe to do this in most mechanisms for quick acid-base steps, which is exactly what this is. Take an H off of a place that has too many and put it on another atom that has lone pairs. Now we have another methanol. It can leave. The oxygen can donate a pair of electrons, stabilize the plus charge that would be created there, and you get yet another oxonium ion. So we're almost done with this mechanism. We're just one H plus removal away from the product. If we use methanol as a weak base, it can take away that lingering H plus right there, neutralize the oxonium, and that's how you get your ketone. This one's also reversible. I just didn't put the reversible arrows there, but you can see a lot of common features where you have oxoniums, things that look like hemiacetals, and only positive charges along the entire mechanism. So that's how you create a ketal and how you remove it. Next, let's look at a creative way that chemists have come up with making ketals from different ketals. This example shows how we can use ketals to actually not protect a ketone, but how to protect a diol. Let's say the diol, like this molecule here, is your more valuable reactant when you're in a laboratory, and you can actually prevent the diol from doing something by trapping it as a ketal. It's still acid-mediated, but it involves changing one ketal to another. And this mechanism gives us a hint. It says that the starting ketal, the dimethoxypropane, first reacts with H plus to lose a methanol and kick out and create an oxonium ion. That's actually exactly what we just did in the mechanism up above. So we're literally going to copy what we just did in the previous example. Draw that dimethoxypropane, draw an arrow from one of the methoxys to the H plus. You'll turn a methoxy into a methanol with a plus charge on it. And now you can lose the methanol. And at the same time, the other methoxy donates a pair of electrons. And there is once again another oxonium ion. And here's where the starting diol can come in and start to react. It's much bigger than two methanols or the ethylene glycol that we used in the first example, but it's still just a diol, and we're eventually going to form two bonds between both alcohols and that one oxonium carbon. It's not crucial to draw which one goes first, but I'm going to assume it's the less sterically hindered one. And then I'll draw it with respect to what used to be the diol and just turn that oxonium piece upside down. So now you have a new carbon-oxygen bond up here, plus charge on this oxygen that used to be the alcohol. And hopefully you can see how the oxonium piece became this piece attached to that diol. So we need to lose this methoxy as a methanol. We can do that with another proton transfer like we did in the previous example. Draw an arrow from that methoxy to this extra H, break the OH bond. You can even write H plus transfer just to show whoever's reading your mechanism what you mean when you do it. That means that oxygen is now neutral. A lot of other stuff in this molecule just along for the ride. A lot of these mechanisms just involves copying your previous structure and changing what's changed. Now we have a methanol attached that can leave, and that neighboring oxygen can stabilize what would be a positive charge. So the plus is on the oxygen, and you get, yes, if you already called it, you get yet again another oxonium. They're everywhere in these mechanisms. So check in and compare this with the structure up above. We still have to make one more carbon-oxygen bond, and we're now set up to do it. The other alcohol can form a bond with that oxonium carbon, draw an arrow from that pi bond to the oxygen, and that's how you make your six-membered ring. You're not exactly done yet. We still have one extra H plus because it was there the whole time, but this is acid catalyzed, so your first step is to put an H plus on. The last step will be to take an H plus off, and we have many things that can do it. It's easy enough to use one of the methanols that just left, and that gives you your neutral ketal in the end. So that's just a different way of getting a ketal onto a molecule where the focus of the starting material is the diol. Let's wrap this up and just look at how chemists use this in syntheses. So here we have a ketone and an ester in the same molecule. We want the ketone to be left untouched, and we want the ester to turn into a tertiary alcohol. It's important to note that esters do not react. Do not react in ketal chemistry. And that's good, because what that means is we can protect the ketone as a ketal, do some functionalization of the ester, turn it into an alcohol, and then deprotect the ketal back into a ketone. This is a synthesis question, so we're not showing curved arrows, we're just going to show reagents. So how do we protect that ketone? Well, we could use the diol that we looked at the very beginning of this lesson, ethylene glycol. Easy enough and very commonly used in the laboratory to take something like a methyl ketone and turn it into this five-membered ring that's a ketal. And then how do you get an ester to become a tertiary alcohol? That's Orgo 1 chemistry. That's a Grignard addition. So in this case, a 2-carbon Grignard followed by some type of acidic workup. The Grignard will add to the ester twice. You'll get a tertiary alcohol, and the ketal stays put. Ketals are very inert to basic reagents, which Grignards are. That means we just need to liberate the ketone from the ketal, and that's just acidic water. So H3O plus you can write next to your arrow, and you've successfully made your keto alcohol in 3 steps from the ketoester. So at this point, I'd like you to hit pause and take a look at the last one. How do you make this molecule with a ketone and an aldehyde turn into a tertiary alcohol with the aldehyde untouched? Okay, welcome back. I find it always useful to draw out the aldehyde, so maybe you did that too. Remember, CHO is an abbreviation for an aldehyde, and I'm just going to draw right on top of it and show what the carbonyl looks like. And you might have wondered, how am I going to do this if both ketones and ketals react? If both ketones and aldehydes react in this type of chemistry? Well, maybe you realized aldehydes are less sterically hindered. So aldehydes, fortunately for this problem, are more easily protected than ketones. So in the presence of one of each, we could selectively trap the aldehyde. I'm going to use the same reagents that we used in the first example, ethylene glycol and a drop of acid. This time, if you just control it stoichiometrically, your ketone will stay put. Your aldehyde will now become a 5-membered ring that looks like that. This is actually called an acetal because we started with an aldehyde, but it's no different than a ketal. Same type of functionality. They're just even easier to make because aldehydes are more reactive. Then to get the ketone to turn into a tertiary alcohol, it's another Grignard addition. This is only a 1-carbon Grignard, so methyl Grignard, followed by an acidic workup. You'll get mixtures of stereoisomers, but we're just going to draw it without any stereochemistry here. We're just interested in the functional groups. And your acetal is along for the ride. And then to turn the acetal back into the aldehyde, just aqueous acid. So there's a couple of examples of how we use acetals and ketals in synthesis problems, and some straightforward mechanisms of how we make ketals and acetals.